So good morning, everyone. This is Yongfeng Zhang from University of Wisconsin-Madison, and thank you for coming. Now I give time to Professor DebRoy, who will give the first talk on the lack of fusion voids, bonding, surface roughness, and residual stress in additive manufacturing. So Professor DebRoy.
Thank you, Dr. Zhang and your colleagues for organizing this meeting. I'm excited to be here to share our work on defect formation in additive manufacturing. The contents are here. 4 topics I want to cover: lack of fusion defects shown here, balling that occurs at high scanning speed, surface roughness that is very common, and residual stress. Then summarize everything at the end. So most of the work has been done by my current and former group members. Special thanks to Tuhin Mukherjee, Bornali Mondol, Yang Du, Meng Jiang, Nick Finch, Quinn Ru, Amitabh De, and Wei Zhang. Lack of fusion defects appear under the microscope like you see in this screen on the left. These are all of different shapes and sizes, and the large ones affect the ultimate tensile strength of the parts. We have plots here of void size versus UTS, and you can see the drop in the ultimate tensile strength for large voids. So they degrade mechanical properties. What you don't see here is that the fatigue properties are also affected by the lack of fusion void. So this is a serious difficulty in the additive manufacturing of metallic components. Our initial work done about 5 years ago focused on mechanistic modeling, in which we solved the equations of conservation of mass, momentum, and energy to find the fusion zone geometry, temperature fields, velocity fields, solidification parameters, and a whole host of other things. We are doing similar things, except here it is for multiple layers and multiple hatches. So what you see here is powder bed fusion using a laser beam of 60 watt power, and it's going at the rate of 1000 millimeter per second, layer thickness of 0.03 millimeter, and hatch spacing of 0.05 millimeter. And this is for 3 materials: stainless steel 316, Ti64, and aluminum silicon magnesium alloy. For the same process parameters, inside the stainless steel 316, some unmelted regions remain, whereas for the casting alloy, aluminum silicon 10 magnesium, the overlaps are sufficient to not have any lack of fusion voids. In short, we know that higher power, higher heat input results in bigger molten pool and reduces the lack of fusion defect. So one would think that it is okay to use a mechanistic model to alleviate this problem. The other thing that is very often done, because mechanistic models are not easily available for everyone on the shop floor, so what is done is trial and errors to reduce the voids. So you change different process parameters and try to do it. Only problem with that is that in additive manufacturing, powders are fairly expensive, and so are the machines of additive manufacturing. So this process of eliminating defects using experimental trial and error is very expensive and time consuming. The voids can also be understood from much higher resolution models that we call powder scale models. And these models typically do a millimeter or 2 of simulation and take an enormously long time, but can resolve the lack of fusion voids. They are very expensive, very time consuming, and they have not been standardized for avoiding these defects. So one other possibility is to use data-driven machine learning that can synthesize the experimental data with physical understanding to provide significant insight. So this is what we are talking about. We have some experimental data and we combine that with models that solve numerically the Navier-Stokes equation and energy equation with appropriate boundary conditions and initial conditions. And these models are built based on our knowledge base of welding, casting, and metallurgy. And we identify the important variables, take all the data we have got, take the output from the mechanistic models and human intelligence, and synthesize all that in the form of a machine learning. And then we can get what we call a lack of fusion index that has all the important variables like width divided by hatch spacing, the pool depth divided by the layer thickness, Marangoni number, which is the ratio of the transport due to Marangoni force divided by diffusive transport, dimensionless peak temperature, which is the peak temperature divided by the liquidus temperature, and Fourier number, which is a non-dimensional number that signifies the transport of heat by conduction divided by amount of heat that is stored in the specimen. A higher value of lack of fusion index can give us the actual lack of fusion in the specimen. And when these values are small, you get very little lack of fusion, or if they are very, very small, you get no lack of fusion at all. And this is valid for a number of alloys and for a very different operating conditions. A paper on this has just been published in Nature Partner Journal, Computational Materials. And one other benefit we get is that we can figure out the hierarchy of important variables. Dimensionless hatch spacing is hatch spacing by pool width. Dimensionless pool depth is pool depth by layer thickness. Marangoni number is the ratio of the transport by Marangoni force divided by the diffusive transport, and dimensionless peak temperature is the ratio of peak temperature to liquidus temperature, and Fourier number, which is the ratio of the heat transported by conduction by heat stored in the specimen. So I am now switching here. Here, what you see is different scanning speed. When the speed is very rapid, you get not a continuous track, but the track breaks up into little balls. So that we call balling in additive manufacturing. And these require post-processing to clean up because of low dimensional accuracy, poor fatigue property, and it hinders also good spreading of the powder after each layer. So this is also a serious problem in the manufacturing of metallic parts by additive manufacturing. So here again, we do some regression analysis with different variables like pool aspect ratio, Richardson number, Marangoni number, surface tension force, solidification time, and the amount of energy that we are putting into unit volume. And we find that the separation between balling and no balling can be very, very straightforward, using this balling susceptibility index to predict the occurrence of balling, and the critical value is about a susceptibility index of 0.5. And a paper explaining the details is available in Applied Materials Today that was published last year. The hierarchical influence of these variables can also be based on different recognized index like information gain ratio, and Gini index. And what we find is that the Marangoni number is the most important variable here. And solidification time energy that is put into a unit volume, Richardson number, the aspect ratio of the fusion zone, and the surface tension force. So most important is the Marangoni number. So modeling can provide us with tools for controlling this type of defects. And the two most important variables are plotted here, Marangoni number and solidification time. And we can see that the blue dots represent no balling, and the red ones represent occurrence of balling. And this is done for a number of alloys for a wide variety of operating conditions. They are all available in details in our Applied Materials Today paper published last year. Surface roughness is another very important problem. Rough surfaces like the ones you see on the two pictures on the right can provide low fatigue life, poor dimensional accuracy, and in extreme cases may result in part rejection. So this is a big problem in additive manufacturing. Current process to avoid this is post-processing, which is expensive and time-consuming. Experimental trial and error process, which is also expensive and time-consuming. Hybrid manufacturing, in which after every layer is deposited, we machine away the surface. This is kind of difficult to control and adds cost. And machine learning, which is very good in many ways, but it's like a black box. So you don't always get very detailed understanding of the physics of the problem. So one other option that we have used is dimensional analysis using raw and computed variables. And this allows us to do rapid screening of experimental data. And because this is very quick and we get explicit relations, we can understand what are the variables that are causing it, and we can take remedial measures. For example, we developed a surface roughness index that we just published in Journal of Manufacturing Processes. And this surface roughness index depends on the enthalpy of melting, the layer thickness, the pull length to depth or aspect ratio of the fusion zone, the heat input in terms of the power divided by speed, and Marangoni force, which is the force due to surface tension gradient resulting primarily from the temperature gradient on the surface. And a paper based on all of this work is available and was just published last week in the Journal of Manufacturing Processes. Again, we can find the important variables, and also we can use this index as a tool for material selection. So here we are plotting the hierarchical importance of different variables like heat input, aspect ratio, Marangoni force, powder diameter, layer thickness, enthalpy of melting, and contact angle. And the most important variable to control the surface roughness is the heat input. And the surface roughness index for different materials for similar processing conditions show that the casting alloy, aluminum, tin silicon, magnesium, is the best, and the stainless steel 316 is most susceptible for rough surfaces. Another very important problem is residual stress and distortion. So what we do here is we take our three-dimensional transient heat transfer and fluid flow model, and we calculate temperature and velocity distribution, temperature field for the entire domain, and velocity distribution in the fusion zone. And we export the geometry, mesh, and the temperature field via a Python script to an Abacus database, and we get residual stress, strain, and the deformation of the domain. So this is a standard program with a high technology readiness level that gives us some confidence about the computed values of residual stress and distortion. By following this technique, we can calculate the stress distribution in different processes, like this is DED GMA, DED laser, and powder bed fusion laser for stainless steel 360. We can also look at the stress distribution in different materials, like Inconel 718 and Ti-6-4, and we can compare the residual stress distributions for different conditions. Now, these are also computationally very intensive, so we train a neural network, and here we are plotting the tensile longitudinal residual stress obtained by neural network with the calculated by mechanistic model. That means our heat transfer fluid flow model combined with Abacus. And this is a viable, very rapid way of getting the maximum residual stress in parts to see whether we need to change our operating variables to lower the residual stress. Another important thing we get out of this type of exercise is feature importance of different variables. And here the preheat temperature seems to be the most important variable to control the residual stress, and followed by power, substrate thickness, scanning speed, yield stress of the material, Young's modulus, thermal expansion coefficient, and thermal diffusivity at room temperature. That is all I have to say. I will summarize in the next minute. Defects in printed parts are very common, and we discussed 4 types of defects: the lack of fusion void, the balling, the surface roughness, and residual stress. And modeling provides a very cost-effective solution based on scientific principles and without need to do many trial and error experiments. And empirical trial and error experiments are expensive and time-consuming, and they are increasingly replaced by mechanistic modeling, machine learning, and dimensional analysis. Often the machine learning is augmented by mechanistic modeling to reduce the number of variables and lower the volume of data needed for the solution. And finally, additive manufacturing solutions based on emerging digital tools. They do not require expensive laboratories or big funding, and allow more researchers to contribute. This is, I think, the future of digital manufacturing, and it's more inclusive. Everyone has an opportunity to contribute. Thank you very much.